Hey everybody! So in this video, we are going to be talking about the unit circle. So here's a basic little blurb from Google. The unit circle, or trig circle, as it's also known, is useful to know because it lets us easily calculate the cosine, sine, and tangent of any angle between 0 and 360, or 0 and 2 pi radians. So when you work with trig functions, sine, cosine, and tangent, you learn those as an introduction, with sine being here. We'll write this down. You learn this with sine of theta is the opposite over the hypotenuse. You learn that cosine of theta is the adjacent over hypotenuse. And then we learn that tangent of theta is the opposite over adjacent. And we introduce those with right triangles. And then what we do is we lead you into what's called your special case right triangles. So that's where you have a 30 and a 60 degree triangle, or you have a 45-45 degree triangle, or you have a 60-30-90 triangle here. So the reason that we say that these are special case right triangles is because these fit in our unit circle. So we use them a lot. So let's see here. If I took this green triangle and I brought it down right here, you see how it fits right inside here. So this is why I'll take this and I'll move it over, and I'll keep pulling this back and forth just as a reference. That's why when you initially start filling out the unit circle, you start with 30 degrees. Now, this sometimes is troubling for some people, understanding what exactly the radian is. So this first radian is pi over 6. Well, you may be thinking, like, what is a radian exactly? Okay, a radian measures the distance around a circle, kind of like circumference. So if I wanted to measure this distance in green from 0 degrees here to 30 degrees, we know that's a 30-degree arc, but I want the distance, kind of like arc length, which you learned in geometry. So this distance would be 1/6 of a radian. Because if I took this green distance here and then I drew it out 6 times, then it would get halfway around the circle. Because we know that in a circle, there are 2 pi radians. Now, I have another video talking about why there are 2 pi radians. So we're just going to assume that this is prior knowledge. If you want to know why there are 2 pi radians in every circle, then I would recommend going back and watching that video. So we'll now take this green dot and then we'll move it back over here as we continue filling out our unit circle. Now, here you'll notice that there are coordinates. So we have an X and a Y coordinate here. Now, you learn that in a 30, 60, 90 triangle, across from 30 degrees is the short leg. And then across from 60 was your long leg, which you learned as X root 3. And then your hypotenuse you learn as twice the length of the short leg. Now, just for simplicity's sake, what we're going to do is we're going to call X here 1. We're going to give it the easiest value to work with. So we're going to say this short leg here is 1, and then that makes our long leg root 3, and that would make our hypotenuse 2. Now, this X value here is going to be the cosine of 30 degrees, not 3 theta. Cosine of 30 degrees. So if I look at my unit circle, cosine of 30 degrees would be the adjacent leg, root 3, over the hypotenuse. So that's why this initial coordinate has a value of root 3 over 2. The y value is going to be sine. So if I'm looking here at 30 degrees and I want sine of 30, then that would be the opposite over the hypotenuse, which gives us 1/2. So there's your coordinates when you're at 30 degrees. Now, there are various explanations as to why you get √3/2 and 1/2. So here's another very common example. Let's say I took that exact same triangle. I took, here, I'll erase these numbers, and I'll take this 30, 60, 90 triangle. You've seen this many times. So this is pretty common, 1, √3, and 2. And then you are always taught in a unit circle, you have a radius of 1. All right? So a radius of 1 in the unit circle, which means that from this point here, the origin, out to this coordinate point here, that hypotenuse of that right triangle should be 1. So we could even do that on this triangle here. We could say, okay, we don't want this to be 2. We want the radius or this hypotenuse to equal 1. Well, then I say, okay, well, what did I do to 2 to make it 1? Well, I divided by 2. So if I do it to the one leg, I have to do it to every leg. So now I have 1/2 and I have √3/2. And then some people will teach you that cosine is always the horizontal distance traveled from the x-axis. They're not wrong. So if you're following this method, that's how you got √3/2. And then the vertical distance from here to this point is sine, or 1/2 here. So if I took these measurements, 1/2 and √3/2 and this triangle, I could move it and place it here, and then this √3/2 would be my x coordinate, and this 1/2 would be my y coordinate. So really, it's whatever is easiest for you. Both explanations provide clear understanding as to how these coordinates come about. So if I took the 45 degree triangle, which we know, and I come and placed it here, we see that there's a perfect fit. So we're evaluating when the angle is at 45 degrees. So here I'll say, okay, this is 45 degrees. And now I want to know the radian value. So again, when we say radian value, we're saying what is the distance around the circle that's being traveled here? Well, that distance is 1/4 of a radian. So here we can say pi/4. And the rules with special right triangles with 45, you learn as 1, 1, and √2. So if the cosine is the x value here, or the x coordinate, and sine is the y, we could just do sine and cosine of this reference angle. So the cosine would be the adjacent over the hypotenuse. So that would be 1. We'll use a color that we can see better here. Let's say 1 over the square root of 2. Well, this needs to be rationalized. So I'll multiply by √2/2. √2/2, excuse me, and this will yield √2/2. So that's going to be the cosine of this 45 degree, meaning that's the x coordinate here. √2/2. And then I'll do the sine of 45, which is opposite over hypotenuse. So I get the exact same thing, 1/√2. So I'm going to have √2/2. And again, depending on what instructor you have, that would determine how you would approach this. I think just taking the trig or taking sine or cosine of this reference angle is simple enough. But let's say your teacher said, okay, let's show that we want this length, this hypotenuse, to go from √2 to 1. Well, it's like, what do you do to √2 in order to make it 1? You can divide it by √2. Well, if I do it to the hypotenuse, I have to do it to each leg. So we've already solved this problem over here on the right. We know that this length is going to be √2/2, and this length is going to be √2/2. So if I use this as the leg lengths of the triangle, when I move the triangle over here, if I were to place the triangle here, you still get the same coordinates because the horizontal distance traveled, the x value, is the bottom leg, root 2 over 2, and then your y coordinate or your sine value is still root 2 over 2. So that's where these values are coming from. And then if I rotate a 30, 60, 90 to get a 60, 30, 90, it fits here. So now we're evaluating here at 60 degrees. And then the radian here, since we know that 60 degrees is twice the size of 30 degrees, at 30 degrees, if I was counting by 1/6, then here, technically, I've traveled 1/6 twice. So I'll just say, what's 1/6 plus another 6th? And that's going to give me 2 over 6, which simplifies to pi over 3. So here with the 60, 30, 90, the same rules apply. We had 1, we had the square root of 3, and we have 2. Now, you can go ahead and apply what we said here. We know that this long leg has a distance of root 3 over 2, and the short leg has a distance of 1/2 if you make the hypotenuse 1. If I don't make the hypotenuse 1 and I'm just evaluating, cosine or x is the adjacent over hypotenuse. So that's 1 over 2. So here, that coordinate would be 1 over 2, 1/2. And then the y value would be the sine of 60 degrees, which is root 3 over 2. So here are my coordinates for quadrant 1. Now, we know that in the unit circle, it has a radius of 1. So if I was looking just at this distance here from the origin over to this point, that would be a distance of 1. And this radius is what's moving around the circle. So here, this would be 0, 1. And I've traveled 90 degrees here. And then I want to say, okay, how many radians would I have to travel to go from 0 right here? Well, we know that this over here on the left, this is pi. So at 90 degrees, I've traveled half that. So I've traveled pi over 2. Now, since we know that we're specifically working with these right triangles, a 30, 60, 90, or a 45, 45, 90, or a 60, 30, 90, those are the only triangles that fit within the unit circle. So as I continue to progress around, these values, these degrees are following the same pattern, 30, 45, 60, 90. So I'm starting from 90 degrees and I'm going to add 30 to get 120. And then if you're counting by 45, 45, 90, that would be 135. And then here, 30, 60, 90, 120. The next 30 or increment of 30 would be 150. And then here we have 180. So we kind of notice this pattern of 30 increased by 15, increased by 15, increased by 30. And then that pattern continues. So we'll write that down here. We're going 30 degrees, increasing by 15, increasing by 15, and then increasing by 30. And this pattern continues. So I could keep going with my degrees. I could say, okay, what's 180 plus 30? Well, that's 210. What's 210 plus 15? Well, that's 225. 225 plus 15 is 240. What's 240 plus 30? 270. And then this pattern continues. 270 plus 30 is 300. 300 plus 15. 315 plus 15. And then 330 plus 30 is 360 degrees. So this is how you complete your way all around the unit circle using degrees. And now what we're doing is we're going to complete with the radians. Well, we should notice that right over here at pi over 6, we're counting by increments of 30 degrees. Now, from 30 to 60 to 90, I'm moving by 30 degrees. So you'll notice that you're counting technically by a sixth. So from 1 over 6 to 60 degrees, this pi thirds is 2 over 6. And then at 90 degrees, that's another increment of 30. That's 3 over 6. So here I can write that, 3 over 6. I'm going to come back and erase it. And then the next increment of 30 would be 4 over 6. The next increment of 30 should be 5 over 6. If I go down 30 again to pi, this should be 6 over 6. And you notice that this continues. So now I have 7 over 6. By 240, I have 8 over 6. At 270, I have 9 over 6. At 300, I have 10 over 6. 330, 11 over 6. And then even here at 2 pi, technically that was 12 over 6, which simplifies to 2. So now all we have to do is come through and simplify our fractions. 4 over 6, that would give us 2 pi thirds. Remember, these are radians, so we have to have our pi symbol here. And then I have 5 pi over 6. 6 pi over 6 is 1 pi. 7 pi over 6 cannot simplify. 8 pi over 6, this can simplify to 4 pi over 3. 9 pi over 6 can simplify to 3 pi over 2. 10 pi over 6 can simplify to 5 pi over 3. 11 over 6 doesn't simplify, so we'll rewrite it to include the pi. So we just completed filling in all of our radians, counting by increments of 1/6. Well, if I move by 45 degrees, I'm counting by increments of 1/4. So every time you do a multiple of 45, you're counting by 1/4 of a radian. So at 90 degrees, this would be 2/4 of a radian, which simplifies to 1/2. We've already done that. At 135, this would be 3/4 of a radian. If I go another 45 degrees, here at pi, that would be 4 over 4, which we've already simplified. Then it would be 5 pi over 4. If I go another 45 degrees to 270, this should have been 6 over 4, which we've already simplified to 3 pi halves. And then at 315, this would be 7 pi over 4. And then over here at 2 pi, this would also be 8 pi over 4, which simplifies to 2 pi. So we've filled out our unit circle using all of our degrees and all of our radian values. Now what we want are the coordinates of each of these points here. Well, you'll notice that nothing's really changing. If I'm looking at pi thirds and 2 pi thirds, these are at the exact same height. So if I have this, pi thirds and 2 pi thirds, all that's happening is this point, pi thirds, is reflecting over the y-axis. It's just moving to the other side. Well, when that happens, all you do is change your x value. So here we should have negative 1/2, and we should have positive root 3 over 2. The same is true here at pi over 4. It's at 3 pi over 4, it's the exact same y value. You're just moving from quadrant 1 to quadrant 2. So the x value is going to change. So we have negative root 2 over 2 and positive root 2 over 2. 5 pi over 6 is in the exact same location as pi over 6. It's just being reflected again over the y-axis. The y value is not changing, just the x. So here I have negative root 3 over 2 and positive 1/2. And then down here at 180 degrees, my radius is on the x-axis, so this is negative 1 and 0. Well, as I continue to go around, 7 pi over 6, this would be created with a 30, 60, 90 triangle, just like 5 pi over 6. So 5 pi over 6 here really is the exact same point. We'll demonstrate this with a line. So from 5 pi over 6 to come down here to 7 pi over 6, I'm using the exact same triangle. I'm just going from quadrant 2 to quadrant 3. So I'm reflecting over the x value. Well, or excuse me, not the x value. I'm reflecting over the x-axis. So when that happens, you change your y coordinate. So here in quadrant 3, x's and y's are negative. So I still have negative root 3 over 2, and now I have negative 1/2. Well, I can apply the same transformation with 3 pi over 4 and 2 pi thirds. 3 pi over 4 is the same triangle being used in quadrant 2 as quadrant 3. It's just below the x-axis. So my x and y values should both be negative. So I have negative root 2 over 2 and negative root 2 over 2. At 4 pi thirds, it's the same point as 2 pi thirds. I'm just reflecting over the x-axis. So the y value here is going to change. So this will be negative 1/2 and negative root 3 over 2. At 270 degrees, my radius is right here on the y-axis. Same logic continues that we just applied. 5 pi thirds is the same triangle being used as pi over 3 up here. So if I made this one long vertical line, pi thirds to 5 pi thirds, what you're doing is you're reflecting over the x-axis. So the y coordinate changes. So I'll have 1/2 and negative root 3 over 2. 7 pi over 4 and pi over 4, same x value. So positive root 2 over 2, reflect over the x, so the y changes, negative root 2 over 2. Same concept here with 11 pi over 6. So this is how you create the construction of your unit circle. Now, if the visual of the radius moving around the circle is giving you a little bit of trouble, let me show you a quick interact. So in this interactive here, we're going to demonstrate what I mean when I say the radius is traveling all the way around the circle. So this interactive is not mine. The author here is Anthony. He created this, and I am using GeoGebra. So here's a radius of 1. And this radius is traveling around the circle. And then you'll notice at certain points, you're creating this right triangle. So that's what we were talking about in the OneNote file there. In the notes, that when I was bringing in the different triangles, you had the 30 degrees, you had the 45 degrees, you had the 60 degrees, and then we came up here to 90. And then I continue in quadrant 2, and you'll notice it's kind of the exact same triangle. This triangle here and this triangle here, if they're both at 60 degrees, they're the exact same size. The only thing that's changing is the x value. And then as the radius continues around the circle, you see how the triangles are being flipped down in quadrant 3 and how they're being moved over in quadrant 4. So if we show values here, I can come up and then I can say, okay, here is 30 degrees right here. And you'll notice that this blue distance is root 3 over 2. And here you have 1/2. And then as I move to 45 degrees, you'll notice that the leg lengths are the exact same. Right? 0.707, 0.707, that's root 2 over 2. And then you go to 60 degrees. And again, you have your horizontal distance of 1/2 and your y value of 0.866, which is root 3 over 2. And then now, when you go from 60 to 120, right, you went to 90, and then from 90, you went to 120. So here, if I did that, you'll notice it's the exact same values as your 60-degree triangle here, except your x value is negative. And if I go down to 135, it's the exact same as a 45 degree, except your x is negative. That's because the triangle's in quadrant 2 and x's are negative in quadrant 2. When I go down to quadrant 3, if I go down to, what was it? 180 plus 30 is 210. So if I go to 210, here's my 30, 60, 90. And both values are negative because your X and your Y value in quadrant 3s are negative. And so this is just a visual representation of what it's like when I say that radius of 1 is moving around the unit circle. So that's going to be it for this video. If you have any questions, please leave them in the comments and I'll get back to them as soon as I can. I hope you all enjoyed this video. Please be sure to hit that like and subscribe button. Share this content, and we'll see you all in the next video.